Howdy everybody, welcome back to Lab Hours. Today we are going to be doing the Estimators mini lecture where we're going to move from talking about parameter or population values into sample or estimated values. The Tommy Triple for today is starting with that exact distinction between parameters and estimators, as I'm going to call them, and I'll explain what that means soon. And then we'll talk about bias and efficiency of estimators, and then we'll talk about consistency of estimators. So let's actually just jump right into it. We're going to distinguish between parameters and estimators using an example that we used a couple of lectures back, right? You remember that we had a variable called test, right? It was test scores, and we said that it was distributed normally with an average or a mean of 75 and a variance of 9, or a standard deviation of 3, right? And I can draw for you what exactly that looks like, okay? It's a nice symmetric bell curve, or at least we're going to pretend that the drawing is. It's centered at 75, and the tails have a height such that it indicates their standard deviation is 3. It's kind of difficult to model exactly in a drawing like this, so we're just going to go with it, okay? Now, up to this point in this class, we have been calling this 75 and 9 mu and sigma squared. They are the parameters of the distribution, right? We've read test scores are distributed as a normal random variable with mean of 75 and variance of 9 or standard deviation of 3, right? That's how we've been reading these things. We have been treating all of our data and everything like that as if we knew exactly these parameters. The trouble is, in real life, we almost never do, okay? Think, if you will, with me for an example, that the company that is issuing this test maybe issues it to all of the high schoolers in America who are juniors, something like that, right? For free, everybody gets to take it. It's like an ACT or an SAT or something like that, right? They make the cost free, they market to all of the schools, it's super big, it's super important, okay? If they are able to get every single junior in America to take this test, will they know these parameters? The answer is potentially still no, right? Let's explain why for a second, okay? If we know that test scores are distributed this way beforehand, we know what the distribution looks like. But what if we don't actually know what it looks like? What if instead of knowing what it looks like, we instead of seeing like this nice curve that I've drawn for you, let me draw a line really quick. What if instead we just see this? This is intending to be like, this would be something like, what's it called? A tree and leaf plot or something like that? Where you just, you've given the test to a bunch of people and you're keeping track of how many times you see a certain score, right? What if this is all you see is just data points? Well, it looks like that distribution could look something like this. Or it could be a distribution that's like this, but we just don't have like enough data points yet, or something like that, right? What do I mean by this? Okay, what's the point of doing this little example? The point of doing this little example is to try to introduce the idea to you that these underlying distributions are not actually knowable perfectly. Reason being, even if the testing company is able to give this test, or it gets it into every high school in America, there might still be some students, some juniors, who choose not to take the test, okay? Their scores may have affected the distribution. Like they might have shown up here or out here, and that might have made a bump, or it might have shifted the mean slightly, right? But they didn't take the test. And then you say, well, what if every single eligible person takes the test? Well, what if there had been one more person to take the test, right? What if there had been one other person, Aside from the fact that getting every single junior in America to take the test being pretty much impossible, someone's going to be sick, someone's not going to want to take it, somebody's going to miss the day, so on and so forth. Even if you could take it from everybody, what if there was a hypothetical next junior, You know, where would they fall? How would they affect the average, right? All of the data collection and all of the measurement tools that we have as people in this world are actually just samples, right? You can say, maybe, what is the average state GDP in the United States? And we could calculate that average from the 50 states we have now. But what if we added Puerto Rico? What if we added DC? What if the Northern California splits into the state of Jefferson? What if Texas gets split into 5 states, you know? What if we combine North and South Dakota so we only have 49? The whole point is that everything that we do in the world is actually just sampling. We don't get full populations, ever. So these parameters, mu and sigma squared, are actually things we can't know for certain, okay? So because the world is actually a sample world, it's not a population data world, knowing these parameters is not possible for us. However, estimating them or getting very close using tools that we've mathematically built to give us those results as their most likely outcome, that is possible, okay? So let's say that we know magically, we have some supernatural knowledge that these test scores are actually distributed with a true mean of 75. You know, on average, if someone takes the test, they will get a 75, no matter how many people take it, no matter where they are. If it's juniors in America, their average is 75 with a standard deviation of 3. Let's just say we know that, even though it's not really possible to know it, okay? Well, what if we know that that's the case, but what if I want to talk to some principal in some high school and he's going to say, well, I don't want the average to be too low, I don't want it to be too variable, because I don't want to demoralize my students or something like that, right? Or maybe we're talking to college admissions people or someone who doesn't know this distribution, and they say, I want you to show me that these parameters are realistic or something like that, right? Or maybe they're not even talking to us and they say, I want to try to figure out what those parameters are so I can see if we want to accept this test at our college or something like that. Maybe what they'll do is they'll take a sample, right? And they'll call it test bar, right? Or test average. That's what we're going to call it now. We've been doing things like X bar, right? X bar is going to be our estimator for mu, or, test bar would be our estimator for mu test, right? Something like that. It will make more sense in just a second, okay? So what I could do is I could calculate some sample average, okay? Let's say, for example, I survey 1,000 juniors in America, and I say, what did you get on this test, and did you take it? And maybe I get 995 responses, okay? So let's say I got 995 responses. Then what I would do is I would do the following. I would do 1 over 995 times the sum from I equals 1 to n, in this case 995, of xi. And what is xi in this case? Well, it's actually not xi, it would be test I. What is test I here? Test I is the test score of the ith student that I asked. So, for example, the first student I asked maybe the first student that I asked got a 54, the second student I asked got an 80, the third student had a 76, the fourth student had a 72, and the fifth student had a 77, right? So I would add up all of the test I's, divide them by the number that I had, and I would call that test bar, okay? So let's just say, for example, that my test bar mean was equal to, in this case, let's say, I don't know, let's say we actually got 75 and 0.2, something like that, okay? Maybe we got 75.2, that'd be pretty cool. Maybe even, 75.1 even. Maybe we got 78, or maybe we got 72, or maybe we hit 80 or something like that, right? We would say, okay, cool. This is an estimate. I have used an estimator, right? calculating the sample mean to try to pin down what the parameter mean, or mu, actually is for this test, okay? This is an estimator. It's like a telescope. And mu would be like a planet. Maybe I can't see mu, the population parameter for mean, with my bare eyes, right? I look up at the sky, it's nighttime, I can't see this mu planet. So I built a telescope to try to parse it out from something that I can see. In this case, I can survey 1,000 students and get 995 responses and, get this number right here. Okay? So test bar got me 75.1 from this sample. But what if that's not good enough for me? What if I took this 1,000 student sample and my boss said, you need to get 1,000 students, and I only got 995, so he says, run it again, okay? And so I'll run it again, and maybe this time I got only 850 responses. So I do 1 over 850 times the sum from I equals 1 to 850 of test I. And maybe this time in the new one, right, and this would be like a dot, 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 dot. And maybe this time in the new one, we had scores 1, 2, 3, 4, 5, dot, dot, dot. And our scores were like 67, 40, 99, 75, 77, something like that, right? And this time I find test bar to be 75, just straight even on the dot. Cool, that's great. But that means that test bar must have a variance, depending on who I ask, right? Because if test bar didn't have a variance, I should be getting the same number. I should be getting like 75, right? If test bar is really a good estimator of this mean, I should be getting 75 every time, right? The answer is no, right? As we can see, depending on who you ask, you might get a different result using the same estimator, right? The 850 here is just n. This is the same telescope, but I've looked in it twice and I've seen two slightly different things. What's up with that? Well, the really interesting thing, think about this, okay? Let's say, for example, that you had the following 10 scores, okay? Let's say that you had 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And I said, okay, I want you to calculate. Let's say this were the population, and I said, I want you to estimate the mean, okay? So we know, in this case, that mu would be equal to 5.5. That's just add up all the numbers, right? And every pair adds up to 11, so when you divide by 10, it's going to be 11 times 5 divided by 10, which is, 5.5, okay? This is what the actual true mean of this is, but what if I only gave you a sample of 3, right? I only gave you 3 observations. So maybe the first time you see 1, 8, 4, and you get x bar is equal to 8 plus 4 is 12, 12 plus 1 is 13, 13 thirds, which is about 4.33. And then maybe the second time you see 3, 4, 10. Well, 10 plus 4 is 14, plus 3 is 17, and then there's 3, right? 3 observations, so 17 over 3, that's going to be 5.667, right? Something like that. And then maybe I give you, you can see, maybe I just give you consistently 3 observations from this 10 observation data set. You can see there's a bunch of different averages that we can get based on if you see 1, 2, 3, all the way to if you see 8, 9, 10. Okay? Or maybe you even see 10, 10, 10, right? Potentially. Maybe these are just potential scores. Who knows? It's a whole thing, right? But what if I gave you in fact, let's say you couldn't even see 10, 10, 10, right? What if I give you 9 observations as opposed to just 3, okay? Let's think about that for a second. Oops. So you can see with just 3 observations, you can get a bunch of different estimates, ranging from 2 all the way up to 9 for mu, even though the true average is right here at 5.5. Now what if instead of that I gave you 9 observations out of the 10? Well, let's see what that could happen. What's the biggest possible one and what's the smallest possible one? So the biggest possible one is if you see 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And that would be what? X bar. 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. This is 27, 27, 37, 46. This would be what? 54? 54, right? 46 to 54. Yeah, 54 divided by 9 is 6, so you'd get an X bar of 6. That's pretty close to 5.5. That's pretty good. What's the smallest possible one, right? So X bar is between, 6 and the smallest possible one in this case would be, if I got everything except for 10, this is 27, 28, that would be 36, that would be 45. My average there is 5. So now we've gone from having the biggest possible estimate being 9 and the smallest one being 2 to the biggest possible estimate being 6 and the smallest being 5. Or adding... Basically what this is trying to show is that adding more observations has actually decreased the variance of X bar in this case, right? And we can see that that's also potentially true here with test bar, right? This is the intuition behind what I'm about to write for you, okay? If you have a variable test that is and it doesn't even need to be test. You'll frequently see it as x here, right? If you have a variable x that's distributed normally with a mean of mu and a variance of sigma squared, then the estimator for its mean is distributed as follows. X bar, which is equal to, 1 over n, the sum of I equals 1 to n of xi. And remember, these xi's are all individual x's being pulled from there, right? That x bar would be distributed as a normal random variable with a mean of mu, but a variance of sigma squared over n. That's really cool, right? We saw why this over n makes sense in the little experiment we just did with our 10 observations. We saw that as you increase n, the variance of x bar, or the range of its possible outcomes, starts to shrink. And the law of large numbers, which is something we have previously mentioned, is what makes it shrink to the actual population average, okay? So this is just one estimator for one parameter, right? X bar is an estimator for mean, or test bar is an estimator for mean of test, right? But you can estimate any parameter. There are formulas to do that, right? There are formulas to estimate variance or sigma squared. And we'll talk about some of those later as we start to introduce the ideas of confidence intervals and hypothesis testing. We'll introduce a bunch of formulas for estimators for a bunch of really common parameters. So for right now, X bar is the only telescope that you've seen. But we'll talk about more soon, okay? For now, take with you the idea that you can use a telescope, some mathematical formula that we have discovered or created or built, something like that, right? To try to estimate these true population or parameters for variables, right? X bar itself becomes a variable. But this variable, this estimator, has a super useful property. In this case, its average is also mean, right? Just by the way that we've built it with the underlying math and stuff like that. And you've seen why that's the case, just in this little mini example here, okay? So the thing to take away from this part of the Tommy triple, and this is the major part of the whole idea, right? That's why we spent 20 minutes on it, is that Up to this point in the class, we've been only considering parameters and formulas for parameters. But in reality, parameters aren't things that we can really see. But mathematically, we can get close to them, right? If this n were infinity, x bar would have zero variance because sigma squared over n would approach, has a lower limit of 0, right? And so if n were infinity, we would only see mean, right? We would only see mu as the result of x bar. X bar would become a constant, and that constant would be mu. That's why it's a good estimator for the true population parameter mu. We get it from x bar when our sample size reaches infinity. But even if our sample size is only 2 billion or 1 million or 10,000, we start to get really, really close because the variance of x bar gets really small, right? It's hitting really close to this mu every time I pull an x bar, right? Every time I pull 850 or 995 for my n, I'm getting more and more likely to hit that exact mu, okay? So that's the idea of using an estimator or a telescope, calling an observation of a telescope, right? Here's one observation of test bar, here's another one, right? This one actually hits mu because we knew that. This one doesn't, but it gets really close, right? So that's the idea of parameters versus estimators. So let's talk about some things that we have assigned as properties of these estimators that help us know if they're useful or not, right? Notice, for example, this is an expected value and this is a variance, right? So what is the expected value of an estimator? Well, in the case of x bar, we would say that the expected value of x bar is equal to 1 over n. Well, so it would be the expected value of 1 over n times the sum from I equals 1 to n of xi, right? And if we know that xi, or x, right, because I just tracks observations, if we know that x is distributed as a normal random variable with mean of mu and variance sigma squared, then I know its expected value is mu for every x, right? Each of these xi's has an expected value mu. So what am I going to do? Well, n is going to be, it looks like a variable right now, but as soon as I decide to get an x bar, I'm going to have to set an n, and it will become constant, right? So let's pull it out. 1 over n times the expected value of the sum from I equals 1 to n of xi. What is that actually going to look like? That's the same as saying 1 over n times the expected value of x1 plus x2 plus x3 plus ... until I get to my xn. And if I want to pass through the expected value operator here, what I'm going to get is I'm going to get 1 over n times expected value of x1 plus expected value of x2, right? We're just distributing the e through using the shortcuts we've done before. Split it the pluses and minuses, and then ... right? Plus the expected value of xn. What is the expected value of x1? It's mu, because it's an x. What is the expected value of x2? It's mu, because it's an x. What is the expected value of ... to xn? It's mu, because it's an x. Okay? So what this all turns into 1 over n times mu plus plus mu. How many mu's are there in these parentheses? Well, there's 1, 2, 3, 4, n of them. So this actually becomes 1 over n times mu, which is equal to mu. Okay, these n's will cancel out. What does this actually mean? How is this helpful, right? Well, first of all, it lets us write the following. X bar is distributed as a normal random variable with a mean of mu, right? We have an expected value of mu here, which is super cool because those line up. What's the variance, though? Well, it's a whole thing, but basically, if you can imagine doing this exact same thing but with a v, we would have to take this 1 over n out and square it when we pulled it out. The variance of each of these x bars, assuming that they're independent, which is a whole thing we'll cover later in the class and in 388, right? But for now, let's just assume they're independent. Each of these, instead of turning into mu, would turn into sigma squared. So I would have n sigma squareds times 1 over n squared, and that's how I got before that the variance was sigma squared over n. Okay, I'll leave that as an exercise to you if you'd like. Make this a v instead if you didn't follow that explanation, right? But it turns into this. So that's pretty helpful. But what does that actually mean? What are these properties called? What do they do? Well, notice that the expected value of x bar is exactly the thing it's trying to estimate. So on average, I expect to see the thing I'm looking for when I look through my x bar telescope. One other thing I could say, or another way that I could phrase that, is that the bias of x bar is 0. I always expect to see what I'm looking for. One way to write that out is the expected value of x bar minus the thing I'm looking for. What is the distance between where I usually end up looking and what I'm actually trying to look for? What's the difference in between it, right? So if I'm consistently seeing 6 feet to the right of some planet, but I want to see the planet, the bias would be those 6 feet, right? In this case, because we've just shown that the expected value of x bar is mu, we get that the bias of x bar is equal to mu minus mu, which is equal to 0. That makes x bar an unbiased estimator for mu. That's super cool. Bias, this formula has this formula right here, okay? Let's say I wanted to take the bias of some arbitrary estimator q hat that was trying to estimate population parameter q. Those are meaningless, they're arbitrary, except in the fact that q hat is an estimator, it's a telescope, and q is the parameter they're trying to look at. So the bias of q hat would become the expected value of q hat, or where q hat usually ends up pointing, and how far away that actually is from q, the parameter it's trying to look at, okay? That's the general formula. The bias of an estimator is the difference between its expected value and the thing it's actually trying to look for. So naturally, you're wondering, well, how do I get from expected value of q bar to q if I don't actually know q? Well, like we did before, q is going to be constructed in some way that it actually uses sample observations of q, or q hat is going to be constructed like that, right? X bar we saw was constructed as follows, 1 over n times the sum of xi, right? Each of these xi's are going to be pulled from this x distribution that has some kind of true parameter that we can't see. In this case, q hat, or q hat would be built with some form of qi in it. Maybe we're summing them, maybe we're subtracting all of them, who knows? You could do pretty much anything as an estimator, depending on what q is and what you're trying to see. But it's in taking this expected value that you're going to get into the world of true q's. Okay, just like we did just a second ago with moving from x bar into the expected value of x bar into the world of parameters by getting all the mu's from all the xi's, okay? So that is how you calculate the bias of an estimator. What if the estimator is biased, though? Here's the question, right? Let's say, for example, that I have some parameter theta that I'm trying to estimate, and let's say I have some theta hat whose formula is unknown, right? I don't know what the formula is, but it's a gross one, something crazy. Maybe it's 6e to the sum of theta I, or something like that. Something that's just gross that I don't want to calculate. And then and maybe there's like some, I don't know, a and b parameters or something like that, right? It doesn't really matter what the formula for theta hat is, except in the fact that it gives us our expected value. And let's say that the expected value of theta hat is actually equal to something like a theta plus b, or something, This formula here is kind of arbitrary. Well, it's not arbitrary, but if you know the expected value of your estimator, then you don't really need to know the actual formula for it. So that's a whole thing. If I were wanting to correct bias. So one thing that you should notice is that this is going to be a huge problem, right? This estimator is going to be biased, okay? Because when I go to calculate the bias of theta hat, I'm going to have a huge problem because I'm going to get expected value of theta hat minus theta, because I'm looking at theta, and that's going to turn into a theta plus b minus theta. That's not going to turn into 0 unless a and b are, unless a is 1 and b is 0, but that's a big assumption to make that we can't make necessarily, right? So is there a way I could make some correction to theta hat to make it unbiased? The answer is yes. Let's think about this for a second. If the expected value of theta hat is a theta plus b, then what would the expected value of theta hat minus b be? Give you a second. Hopefully you can see that that expected value would be the same as the expected value of theta hat plus the expected value of negative b. And since we said before that b and a were constants, once you take a sample, that will turn into a theta plus b minus b, which is equal to a theta. Well, that's pretty cool. But that doesn't fully fix our problem because we need this expected value to turn into theta by itself. Well, what if this is the expected value of theta hat minus b, what is the expected value of theta hat minus b over a? Hopefully you can see, and if you can't, I'll leave this as an exercise for you, remembering that a and b are treated as constants here in this expected value. But this would turn into theta, right? This would correct the a theta that was still left over. How does this make any sense, right? Well, the really cool thing is that that becomes a function of theta hat. So whatever theta hat is, you could call this theta hat star or something like that, right? Theta hat star could be a function of theta hat. Whatever theta hat is as a function of theta, right? Just like how x bar is a function of x, xi specifically. Maybe theta hat star is just the way that you've corrected your telescope or you've adjusted your telescope, you've fixed your estimator. That could be equal to theta hat minus b over a, right? What would the expected value of theta hat star be? Would be equal to the expected value of theta hat minus b over a, and because we would be taking that expected value in terms of theta, b and a would be treated as constants, and just like we've shown down here, it would turn into theta, okay? So long as, this is still true. So we've shown you what bias of an estimator is, and that will sort of cover how you can correct it if you see it. So be on the lookout for that. But one other property that we need to talk about is efficiency, really quick. And efficiency is fairly relative, okay? It has to do with variance, right here, the variance of an estimator. And the only thing that efficiency tells us is whether one estimator is more or less variable than another estimator. So, for example, consider the following two estimators that potentially can give you, an estimate for mu. First of all, we have our classic x bar, which is 1 over n times the sum of xi. And then let me give you the following, okay? Call mu 1/2 equal to, 1/2 x1 plus 1 over n minus 1, the sum of xi, where I is equal to 2 to n, right? So basically what this is saying is x bar is saying weight every observation equally, right? Take every xi and divide it by 1 over n. And what mu 1/2 would be saying would be give half of the weight of your average to the first observation and then split the rest of the weighting evenly across all the rest of the observations. So this could be 1/2 x1 plus 1/2 x2, or it could be 1/2 x1 plus 1, I don't know, let's see, if n were 3, that would be Oh, that's actually wrong. Is it? Wait. N is 2, 1 over 1. Yeah, so this would actually need to be like 1 over n minus 2, huh? Right? Because if I have 2 observations... No, something's wrong with that formula, but that's okay. Oh, I see what it is. Hold on. If I have 3 observations left, this would be 1/2 x1 plus 1/4. Yeah. It should be n plus 1. 1 over n plus 1 from I to 2 to n, okay? So this would be 1/2... No, that's not right either. What the heck? Hold on. Well, some formula that does that. In fact, let's just pretend, for example, there's only 3 observations. So x bar would be 1/3, mu 1/2 would be 1/2 x1 plus 1/4 x2 plus 1/4 x3, something like that, okay? Where if there's 3 observations, here are my 2 potential estimates for mu. The question is, which of them varies more? Because I would theoretically want to use the one that varies less because it will be giving me mu more often, right? Or be more likely to give me mu. I'll leave this as an exercise to you, and I think it's actually on the homework for the class. These are both unbiased estimators, but one of them is more efficient than the other, as follows. The variance of x bar, as we showed before, would be sigma squared over n, which is going to be 1/3 sigma squared in this case, right? Because there's 3 observations. What is the variance of mu 1/2 here? Well, mu 1/2, the variance of mu 1/2 would be equal to the variance of 1/2 x1 plus 1/4 x2 plus 1/4 x3, right? And that would be equal to the variance of 1/2 x1 plus the variance of 1/4 x2 plus the variance of 1/4 x3, right? Easy peasy. Then I'd pull out my constants and square them. That would be 1/4 the variance of x1 plus 1/16 the variance of x2 plus 1/16 the variance of x3. What are the variances of x1, x2, and x3? Well, they're x's, so their variance is sigma squared. So that turns into 1/4 sigma squared plus 1/16 sigma squared plus 1/16 sigma squared, which is equal to 6/16 or 3/8 sigma squared. And then the question is, which of these is bigger, right? 1/3 is 0.333. 3/8 is 0.378. So we see that the variance of mu 1/2 is 0.375 sigma squared, but the variance of x bar is only 0.333 sigma squared. So x bar is more efficient. Its variance is smaller. Does that make sense intuitively? The answer is yes. Let's go back to our 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 world. If I gave you 1, 2, 3, x bar would give you 2. If I gave you 3, 2, 1, x bar would give you 2. If I gave you 1, 2, 3, though, what would mu 1/2 give you? It would give you 1/2 plus 1/2 plus 3/4. It would give you 1 3/4. But what if I give you 3, 2, 1 instead? That would give you 1.5 plus 1/2 plus 1/4, or 2 1/4. So even with the same numbers, you would get a different mu 1/2 estimate because this weighting is different based on the order of observations. So there's more possible outcomes for mu 1/2 here as an estimator, so of course its variance is going to be bigger. The variance of x bar only depends on which observations you see. It does not depend on the order in which you see them. But the variance of mu 1/2 depends on both which observations you see and in which order, right? So this concept of efficiency is where we say that x bar would be a better overall estimator in general than mu 1/2 because it is more efficient. It has a smaller variance. But there are still cases where you might want to use mu 1/2. It depends. And you'll talk about that more later in the class and also in classes like 388. You might want to use an estimator like this at times, okay? So that covers the idea of bias, how to find bias, and how to calculate efficiency. Just take the variance and see which one has the bigger variance. The one with the smaller variance is the more efficient estimator. And theoretically, intuitively that makes sense because When I look in my telescope, the one with smaller variance is the one I'm going to be seeing the thing I'm looking for in more often. That's pretty much just all how it goes, okay? So let's check that one off. And now let's talk about consistency. This is just going to be one more minute. Consistency is just a quality of an estimator that goes as follows. We want the bias. Let's call our estimator star hat here. If the bias of star hat approaches 0 and the variance of star hat approaches 0 as n approaches infinity, then star hat is consistent. Okay? Those are just two qualities, okay? So, for example, let's take a look at x bar. What is the bias of x bar? Well, that just straight up is equal to 0. It's not dependent on n at all, okay? What is the variance of x bar? Well, we've shown that the variance of x bar is sigma squared over n. As n approaches infinity, where does that variance go? Well, it approaches 0 because this denominator is going to get super huge and sigma squared is never going to change, right? It'll become a constant. So x bar is a consistent estimator. Super cool stuff. Now, if we were only ever allowed to get 3 observations, right, this wouldn't make any sense. Variance could never approach 0, okay? This is just how you check for consistency. It's these properties. Does the bias approach 0? Does the variance approach 0 as n approaches infinity? That's it. If so, your estimator is consistent, and you will spend considerably more time on that in 388, in later classes, in later studies of probability and stuff like that. So that is going to cover everything, and today is long because this concept is probably the most difficult one to get. We are no longer in parameter land. We don't know these numbers anymore. We've been pretending that we do, but we no longer do. Okay? Instead, we are in the world of samples and estimators now. So, get used to it. That is the mini lecture for today. We covered parameters and estimators, the difference between them. We talked about calculating the bias and efficiency of your estimators or your telescopes. And then we talked about this cool quality called consistency that makes it really nice, that makes a given estimator really nice. If you can get a consistent estimator, you're in an amazing spot, right? And that's going to be it for today. Join us next time when we talk about confidence intervals in our mini lecture. And you can see I'm not quite ready for that one yet. So let's go ahead and do it. Thank you so much for watching. Have an excellent day, and hope to see you next time. Of course, if you have any questions, go ahead and email me if you're in the class at tmorg.ta@gmail.com, and if you're not in the class at labhours@tmorg.org. As always, comments, likes, shares, you know the drill. Thanks for stopping by. We'll see you next time. Bye-bye.